The motivation for this project was to learn FPGA and Verilog programming language and implement an arcade-style interactive Skeeball game using finite state machines and infrared sensors.
Hi, so our team name is Kokumalan. My name is Mariam Farid and I'm from C.
My name is Aisha Kashif and I'm from CS.
My name is Rohan and I'm from CA. My name is Amar Rahman and I'm from CA.
And this is our project, Skeeball.
This is what our state diagram looks like. When our input start is 0, we are at the start screen. When it becomes 1, we go to a countdown, and then when the countdown ends, we go to our game screen, at which point we wait for the game screen timer to end. When it ends, we go to our end screen. When we are at the end screen, we stay there until and unless our start becomes 0, and if the start remains 1, we stay at the end screen. Additionally, if at any point the start becomes 0, we go straight back to the start screen. This also works as our reset.
User flow diagram for this design starts off with the FPGA loading and displaying the start screen with the Skeeball logo only. It will continuously check if the V16 button is pressed or not. If it is, it will display the transition screen with 1, 2 and 3 go, which take about 4 seconds, and if the V16 button is not pressed, it will stay at the start screen only. After the transition screens, the game screen with the 2-minute timer and score and the multiplier will be initialized, and after that, it will continuously check if which IR sensor is triggered or not, and will calculate the score respectively. For example, for the 100 calculating IR sensor, it will increase the score by 100 multiplied by the multiplier that is currently.
This is our main game screen where we have Skeeball blinking to the name of our game. Using a 3 to 1 go transition screen, we move on to our main game screen, in which we have a 2-minute timer running at the top. We also have a score, 5 score, and we have a bonus multiplier also showing. The score will increment by 100, 250 or 400 depending on which hole you put your ball into. The bonus logic works like this: if your ball goes into any one of the holes, 100, 250 or 400, an in-game timer starts for 5 seconds. In those 5 seconds, if your ball goes into either 250 or 400, your new score is first multiplied by the bonus multiplier, and then it is added to the total score. When the 2-minute timer ends, we move on to our end screen where we have a display of times up showing and our final score.
In this design, we have 2 inputs. One is the V16 button and the other is the IR sensor. The IR sensor continuously sends a 0 or 1 signal to the FPGA, and for the V16 button, we have used it for the start screen to the game screen transition. For the output, we have mainly used the VGA. The VGA is controlled by the clock signal. We have converted the 100 MHz clock signal that comes from the FPGA to the 25 MHz clock signal that is required by the monitor. For it, we have used like four respective pins for each color, that is red, green and blue, and we have used like H-sync and V-sync as pins as well in this VGA.
Okay, so for our score logic, we have a 5-digit score which takes 3 inputs: 100 input, 250 input and 400 input. So for example, if our ball goes into the hole of 250 score, so our score will increment by 250. And how the logic works is that the input is translated to the corresponding score value, and we have a variable which stores our score, and it takes the input value and mods it by 1, 10, 100, 1000 and 10,000 for each corresponding digit, and adds it to our score. And the display works in the same way that it mods the value and takes the digit 1 by 1 and corresponds it to the number.
So for the timer, we take advantage of the fact that we're working with 25 megahertz. So what that means is that in a single second, we complete 25 million cycles. So what we do for the timer is that every 25 million cycles, we increase the counter by 1 and keep increasing it every 25 million cycles until it reaches 120, at which point our timer ends and then we go to end. On the screen, we subtract the current count from 120. So to display the minute tens, we divide by 60 and then divide by 10 again. For the minute ones, we divide by 60 and take the mode from 10. And for the second tens, we divide by 60, we mod it by 60 and divide it by 10. And for the second ones, we mod it by 60 and mod it by 10.
Whenever we input 250 score or 400 score, a 5-second timer will start, and if during those 5 seconds we input 250 or 400 again, then the bonus will increase by 1. And then each score that we input next will get multiplied by that bonus value and will get added into the score. 5-second timer, which is obviously set to 25 megahertz clock, and then after the timer begins, it will detect that if our input is 250 or 400, it will take that corresponding value and multiply that value stored in our score and add it bit by bit, modulus and mod it and add it into our score to display. During the 5 seconds, if we do not give it any input 250 or 400, then the multiplier will start decreasing by 1 until it reaches the minimum value, which is 1. Also, the maximum value for our multiplier is times 3.
Regarding the challenges that we faced, first was material procurement for our hardware. It was difficult for us to find the right size and the right type of wood for our hardware. Secondly, figuring out the correct placement for the IR sensors was a hassle. We had to tweak their positions multiple times in order to ensure accurate ball detection without false streak. Last but not least, we initially tried implementing tile flipping and checkerboard transitions, shear timing errors and glitches. So we removed that idea and we switched to a relatively simpler 3-2-1 go transition screen.